Hi everyone, I'm Takis, and today we'll present you on the epigenetic changes in cancer. So, as an overview, cancer is the abnormal proliferation of cells and the spread of these cells to other body tissues or other body parts. So, as we know, cancer is very dangerous and it can lead to a lot of bad things such as death itself if left untreated or if treatment is not available. So epigenetics is described as heritable changes in gene expression that is not due to DNA sequences. So essentially, what this is saying is that epigenetics is a result of gene expression that is not encoded in the DNA sequences. So the link between cancer and epigenetics is that cancer has multiple epigenetic abnormalities and genetic alterations. These alterations can act at all stages of cancer to enhance tumor progression. So currently there are several challenges with the development of therapies for cancer. So the first one is that cancer is an heterogeneous group of diseases, and this means that there are different types of cancers. And also, one let's say two persons have breast cancer. The breast cancer that one person has isn't the same as that which another person does have. So it changes from person to person and also from let's say body side to body side. And therefore this makes it extremely difficult to develop a quote unquote cure for cancer or development effective treatment. In addition, there have been many cases where cancers have become resistant to drugs or to drug treatment. A good example is resistance to Herceptin, which is used to treat HER2 positive breast cancer. In addition, there's a lot of health disparities as it relates to cancer, and this health disparity means that certain ethnic groups they're not well educated on cancer, or they're not provided with the resources to help them to have access to information on cancer or information on cancer diagnosis, and this leads to them finding out that they have are seeking treatment for cancer when it is too late. And in addition, not everyone the proper treatment or continue with the proper treatment for their cancer as prescribed by physician or so on. So epigenetic changes are known as epimutations. So in cancer, these epimutations act to independently silence tumor suppressor genes, and this leads to the two the required second hit. So as we discussed from the NUD seems to hit hypothesis. So some persons are born with let's say a mutated one version of the tumor suppressor gene mutated, and what epigenetic silencing does is that it renders the other copy of the tumor suppressor gene inactive, and this rendering of it inactive then allows for the initiation of cancer. So the most common epimutations in cancer are DNA methylation, histone modification. So in normal cells, DNA methylation is shown by the fissure here at the CPG islands, and this leads to basically the formation of the post chromatin state and the repression of the gene expression. So in cancer, there is genome-wide hypomethylation, and this hypomethylation it promotes genetic instability and the activation of proto-oncogenes. So genetic instability means that there are multiple movements going on in the genes or in the chromosomes. This can be translocations, mutations, and this process basically leads to activation of proto-oncogenes. And the activation of proto-oncogenes basically increases the chance that a normal cell will transform into a cancer cell. So in cancer, there's also site-specific CPG island promoter hypermethylation, and this hypermethylation, um, as shown here, it causes the chromatin to condense, and this basically silences your tumor suppressor genes. So the level of gene regulation that this act has is the promoter availability, because if the chromatin is basically too condensed, this prevents your transcription factors, your RNA polymers from getting in to and having access to the promoter in order to transcribe the gene. So another epigenetic modification in cancer is histone modifications. So two main ones that are seen is that there's loss of acetylation, and also there is increase in methylation of your histones. So this loss of acetylation is mediated by overexpression of histone deacetylases in cancer. And the overexpression of these deacetylases results in the removal of acetyl groups on histones. And as we know in class before that histones both act in the sense and trans manner to basically increase promoter availability. However, we know that methylation can act both to promote increase transcription and decrease transcription. However, in this case, the hypermethylation in cancer is due to the dysregulation of histone methylase, and this results in aberrant gene silencing. And a good example is the EZH2, which is a histone methyltransferase, and this is overexpressed in both breast and prostate cancer. So overall, we've seen where DNA methylation and histone modifications are two forms of epigenetic changes in cancer, and these can work independently or together to change the gene expression profile of cancer cells. So here's a picture from our book which shows how histone modifications can change your chromatin state and therefore affect gene expression. So in cancer, histones are usually hypomethylated. So most of the methyl groups are. I'm sorry. In cancer, histones are most likely hypoacetylated. So this means that a lot of the acetyl groups are actually removed, or histone is deacetylated specifically. And this deacetylation of histone basically results in your closed chromatin state. And this closed chromatin state basically reduces promoter availability. And in cancer, the histones are also hypermethylated, and this hypermethylation leads to closed chromatin state and also reduces promoter availability. So we see that the silencing mechanism which epigenetic modifications play in cancer leads to the rigid chromatin state and therefore less expression of genes. These alterations in gene expression, they promote tumor development. However, research has shown that these epigenetic modifications are not random. However, due to previous alterations in the central epigenetic control machinery, or the previous alteration in epigenetic control machinery results in these specific epigenetic mutations. However, on the bright side, these epigenetic modifications are reversible, and this makes them a good target for therapeutics. These are my references. Thank you.